Okay, this is 2016 FRQ number 1 in the graphing calculator portion. Okay, so number 1 here has a data table, and it says water is pumped into a tank at a rate modeled by W of T equals 2000 e to the negative T squared over 20 liters per hour between 0 to 8 hours. And water is removed from the tank at a rate modeled by R of T liters per hour, where R is differentiable and decreasing between 0 to 8 hours. So R of T is this table in front of us, and WT is a function. Okay, so water is pumped in with WT, and water removed, R of T. Selected values of R of T are shown in the table above. Initially, at T equals 0, there are 50,000 liters of water in the tank. Okay, so first one says, A, estimate R prime of 2. Show the work that leads to your answer, indicate units of measure. So it wants you to take the derivative of 2, but you don't have 2. So we're going to use slope. We're going to use y2 minus y1 using the 1 and 3 that's sandwiching the 2, and using this as my y2 and y1 and figuring out what R prime of 2 is. Okay, so for part A, R prime of 2 is equal to 950 minus 1190 over 3 minus 1. That would give us negative 240 over 2, negative 120 liters per hour. So because this is a rate of R of T, so liters per hour. So that will be your measurement. Okay. All right. Next, it says use a left Riemann sum. I guess I'm going to erase these markings. Use an LRAM with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. Is this an overestimate or underestimate of the total amount of water removed? Give a reason for your answer. So let's find the LRAM first. So LRAM means we don't use the last. All right, so that means we don't use the last y value. So between the first 2 intervals, that's a 0 and 1 multiplied by 1340. Okay, so make sure I can see all of this information. So using LRAM, it's going to be 1 times 1340 plus, between 1 and 3, that's a difference of 2. And then using this y value, 1190, that's my LRAM. And then between 3 to 6, that's a difference of 3. Using the LRAM here, 950. And then between 6 and 8, that's 2. And then using 740. All right. So we're going to add all this up. I get 1340 plus 2223.80 plus 1950 plus 1480. Okay. Oh, whoops. I made a mistake. Sorry. No wonder. That looks weird. Okay, sorry. That would be 3 times 5, 15, 28. Yeah, 2850. Okay, add them all up. That's a total of 8,050 liters. Okay, so this is an over and under estimate. So we gotta read our problem here. Our problem here says this function, this R of T is differentiable and decreasing. That's the most important thing. So if my function is decreasing, no matter whether it's this way, whether it's concaving up or concaving down, my LRAM is going to be like this. Right, so LRAM is going to be an overestimate. So you're going to explain the fact that because this function is decreasing, so R of T is decreasing. Therefore, this is LRAM is an overestimate. Right? If it's increasing, then LRAM will be an underestimate. Okay? All right. Moving on. Sorry. Part C says, use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Okay, so let's see. What did we start out initially? Initially, we had 50,000 liter. Okay, so initially we have 50,000 liter. Then water is going to get pumped in at a rate of W of T. So at this rate, 2,000 e to the T negative T squared over 20. So 2,000 e to negative T squared over 20 dt from 0 to 8 hours. That's how much water is going to pump in. Minus R of T for 8 hours, which we used LRAM to approximate in part B. So we're going to use this answer right here, this 8,050 liters. That's how much water is being pumped out. So 8,050, right? So that would be the amount after 8 hours. Okay, so you do need your calculator to figure out this integral, right? So let's find our calculator. Okay, so we're going to use our calculator to figure out the integral. So we go math 9, right? My integral goes from 0 to 8. My equation of 2,000 e to the negative t squared over 20. Don't forget your same variable, dx. All right, looking good. Enter. For some reason, mine's giving me this awesome fraction, so I am just going to change it to a decimal. So I have a nice answer, 7,836.195. Okay, all right, 7,386.195. Oh, and don't forget, I started with 50,000, right? Plus pumping in this 7,836.195, and then subtract, take away the pumping out. How much did I pump out? 8050. So how much is left in the tank right now? 49,786.195. All right. So all right, so that's how much is left at the end of 8 hours. Okay, looking good. Last part. So between 0 to 8 hours, is there a time at which the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not. So I'm looking for when water being pumped in, W of T, when is it equal to R of T? Right? So because R is not a function, you cannot just simply set the equation equal to each other and solve. So what's another way to look at it? Another way to look at it is to look at it as one function. So let's subtract the R of T over. This is a very weird trick that, we haven't done before. So let's subtract R of T over. And now we have W of T minus R of T equals 0. So I'm asking you, when is it possible for W of T minus R of T equals 0? Right? Is it possible for this function, W of T minus R of T, is it possible to equal 0? Okay, we're trying to figure out, is there a value, right, in between, in this function of pumping in the water between 0 to 8 hours, right? So in the beginning is 0 hours, at the end is 8 hours. Between 0 to 8 hours, is there a time where WT minus R of T equals 0? So you got to check. We're trying to use IVT. We're trying to use intermediate value theorem to prove that this is true. So we got to check the beginning. We're going to check the first endpoint, 0, right? So we're going to check the first endpoint. So W of 0 minus R of 0. That's the beginning. And then we're going to check the end, W8 minus R of 8, and see if I can see some correlation there. Okay, so W of 0. So W0 is the, what does it say W0 is? So W0, if you plug it in, if you plug 0 into this equation up here, you will see e to the 0 is going to be 1. So you get 2,000. So W0 is 2,000. Very nice. Minus R of 0, let's look at the table up here. R of 0, 1340. Okay, so 1340. So in the very beginning, this is 660, right? Doesn't matter. You'll see in a minute why it doesn't matter. Okay. What about W8 minus R of 8? So W8 minus R of 8. W8, if we plug in 8 into this function, so 2,000 times e to the negative 8 squared over 20. So W of 8 equals 2,000 e to negative 64 over 20. I don't know what that is. Let's check. All right. So let's see. So 2,000 e to the negative 64 over 20. What is that? 81.542. Okay, 81.542. Let's remember that. So 81.542. Okay, so 81.542 minus R of 8. What is that on the table? The table says R of 8 is 700 here. Okay, so 700 minus 700. You don't even need to work this out. You can see that this is going to give me a negative value. And again, this, I said it didn't matter that it's 660. You know that this was going to be a positive value. So by IVT, you see that in the beginning, I started out positive, and then at the end, I ended up negative. So somehow through this function, through this continuous function, I must pass through 0. So because I showed that the beginning is positive and the end is negative, then somewhere in the middle, it must cross through the x-axis. So by IVT, W of t minus R of t must equal 0 in between 0 to 8 hours. Okay, all right, that's it.